So, okay, now I hope that you understand the main concept of CP and CPK and how you will calculate CP value and CPK from a specific data, because in my previous lectures I already show you manually that how you will calculate CP and CPK, and now you also know how to use Q1 macros, which is an Excel add-in, in order to construct a histogram, in order to construct the specification level, and to check that where the specification of the data is capable or not capable. So in this lecture I am just going to show you to solve some more example in order to further clear your concept about 6 sigma, 3 sigma, 4 sigma and 5 sigma. So you can see that capability index CPK, which show how well the performance measure fit the design specification based on a given tolerance level. So normally, because in the formulation we use normally 3 sigma, we can also change this sigma. A process is K sigma capable. Now it's on you. In order, if a company, if a specific organization claim that our company, our organization, our production is capable of K sigma means let's suppose 3 sigma. Then what you need to do? You need to collect data, you need to collect some sample, and then you check that is that organization is capable for 3 sigma, 4 sigma, or for 6 sigma or not. So normally, generally we can write this x bar plus K sigma is less than or equal to upper tolerance limit or upper specification limit, and x bar minus K sigma will be greater than or equal to lower tolerance limit or lower specification level. Or you can also write this, if you take this, if you divide this with this, so it will be upper tolerance limit minus x bar, which is mean divided by K sigma, 3 sigma, 4 sigma if it is greater than 1, and x bar minus lower tolerance limit divided by K sigma if it is greater than 1, then it's mean the process is capable for that sigma. So now this is general formulation. It is a 3 sigma, 4 sigma or 5 sigma or 6 sigma. It depends on you and it depends on the claim which they already made that we are producing, we are fulfilling 3 sigma level. Another way of writing this is to calculate the capability index is CPK. So you also know this is the formulation of CPK, x bar minus lower tolerance limit divided by K sigma, comma upper tolerance limit minus x bar K sigma. So until now we have mentioned different example that CPK when it is less than 1, which is mean that the process is not capable at the specific sigma level, 3 sigma, 4 sigma or 5 sigma. If it is greater than or equal, mean the process is capable at that sigma. We said that the process is accurate if its mean is close to that target T. We said that process is consistent if standard deviation is low. So as I already mentioned that standard deviation basically it's a risk factor. It's basically showing you, it's giving you an indication of risk. When this standard deviation value is very high, it means there is too much risk involved. It means that the process will not be capable. So that is why when the standard deviation of a specific process is low, there is a chance that the whole process of that specific organization will be capable for that. So now there is a simple example. In this example, we want to construct the capability index CPK in order to check that is this process capable or not. So you can also see from the figure that this process is not capable. Why? Because most of the normal distribution area is outside from this. So when it is outside from the lower tolerance limit and upper tolerance limit, it means it's not fulfilling the thing. So x bar is 10 and sigma is 0.5 for this, lower tolerance limit is 9 and upper tolerance limit is 11. So CPK is equal to minimum. So you already know the formulation. The formulation is x bar minus LTL divided by K sigma. So we want to check this for 3 sigma. That is why we multiplying with 3 sigma. If you want to check it for 4 sigma, you can also calculate. So if a process is not capable for 3 sigma, how it will be capable for 4 sigma? Because 4 sigma level is very high than 3 sigma. As I already mentioned that parts per million, how many will be defect while using 3 sigma, how many parts will be defective while using 4 sigma, and how many million parts will be defective in 5 sigma and 6 sigma. So this process is not capable, and you can also check, you can also judge it from the figure. This is another example. This is just like this one, but we change only the mean. The mean before was 10, Now we want to change the mean, which is 9.5. The sigma level, tolerance level, and the upper tolerance level are same. So when you put these things in this formulation, x bar is 9.5 minus lower tolerance limit divided by 3 sigma. So we want to check it on 3 sigma. So Cpk value is 0.33. Once again, because you just changed the mean, so it doesn't matter. There is the spread, the deviation is same, but the mean is changed. But once again, this Cpk value is less than 1. So the process is not capable. There is another example. Because in this example, we also changed the standard deviation. So you can see this figure and in this figure, there is too much different. This one is a little bit narrow, this one is a little bit peak, but this one is a little bit dispersed. That is why it's dispersed, because in the previous one, the standard deviation was 0.5. But now the standard deviation is very high, very big too. So when we calculate Cpk for this, which is lower than this one, so you can see this is 0.33 and this is 0.16. Because when the standard deviation value is very high, it means there is too much risk involved. So it's also showing you that the process is not capable at this 3 sigma level. So if it is not, so it will not be able, that it will be, process will not be capable for 4 sigma, 5 sigma, 6 sigma. Maybe it will be capable for 2 sigma. So you can also check it for 2 sigma. So for assignment, you also need to check it for 2 sigma. Maybe it will be capable for 2 sigma. Okay. There is another example. Consider the capability of a process that puts pressurized grease in an aerosol can. The design specs call for an average of 60 pounds per square inch of pressure in each can with an upper tolerance limit of 65. So, mean the design specification is that there will be the average mean will be 60 pounds per square inch, and there will be an upper tolerance limit of 65 psi. So, mean average in every can you can put 60 pounds per square inch, but in some cases you can increase the tolerance. Upper tolerance limit is 65. Okay, so this is a sensitivity thing that you can increase 65, but if you increase it from 65, then maybe that can will be burst out. So 65 is the upper tolerance limit and 55 is the lower tolerance limit. A sample is now an inspector visited that company which filling grease in the can. So they just collect a sample from the production of that organization, from that company, and they found that the can averages. So from the sample x bar, they calculate x bar. They calculate it is 61. So this is the sample mean. Okay, 61 psi with a standard deviation of 2 psi, and they also calculate from that sample that the standard deviation, the dispersion in the data is 2 psi. Now the question is the process capable at 3 sigma level? So now you need to check. Being a quality manager, being a quality expert, being an expert in the 6 sigma, you will be able to solve this. That is the process capable at 3 sigma level or not? What is the probability of producing a defect? So this is very interesting question. Maybe your manager tomorrow, they will ask you if this is not capable, or if it is capable, then what is the probability that you will producing a defect? So you need to extract the data from this example. As they mentioned, the design spec call for average 60 pounds per square inch of pressurized can with an upper tolerance. So this is my upper tolerance, which is 65. Lower tolerance is 55. Sigma, the standard deviation, the sample is 2, and the average mean, the mean is 61. So now let me solve this. So this is the data which we have extract so far. So Cpk formulation is minimum x bar minus LTL divided by 3 sigma. UTL minus x bar 3 sigma. So x bar is 61 minus lower tolerance is 55 and 3, because they already mentioned that check it for 3 sigma. If they want to check it for 4 sigma, you need to multiply 4. If they want to check it for 2 sigma, if the industry claim that we fulfilling 2 sigma level, so you need to put 2 sigma. But now they ask 3 sigma, so that is why we calculating for 3 sigma. So 3 into 2 will be 6, 3 into 2 will be 6. Now when you interpret it, when you calculate it, when you simplify it, it will be 0.667. So we will choose minimum 1, minimum min. So no, the process is not capable at 3 sigma level. So the process is not capable because Cpk value is less than 0.667. Now the second question is, what is the probability of producing a defect? Now we want to calculate the defect probability. So if you understand the basic concept of normal distribution, you will be able to find this defective probability. So this is my 55 lower tolerance limit, this is my 65 upper tolerance limit, and this is my normal distribution. Mean is 61, the data which we have collected so far. Now, so in this lower tolerance limit and upper tolerance limit, mean the cane whose are the mean degrees which are inside the cane, which amount is 55 and 65, they will be considered as an accepted one. They will be considered as in the accepted region. They will be considered as an effective. But those whose value is less than, let's suppose in a specific cane, you randomly select a cane and you check the amount of grease in that cane, let's suppose is 54. So it will be in this region. It will not be in this region. Or if you randomly pick and you check the amount of gasoline, the grease inside the cane is, let's suppose, 66. So it is outside from this. So now we want to calculate this area and this area. Okay. So we can easily calculate probability of defect is equal to probability of x is less than 55 plus probability of x is greater than 65. So that is why I just write this x is greater than 65 this area and x is less than 55 this area. Now you can also know the probability rule that, for example, if I throw a die, the probability of getting 1, 2, 3, 4, 5, 6 will be 1 by 6. Okay. So if I say that the probability of 5 and 6, what will be the probability that the number appear will not be 5 and 6? So if you calculate the probability of 5 and 6, so the probability of 5 and 6 will be 6. So because this is a winning situation, so probability of 5 or 6 will be 1 by 6 plus 1 by 6. It will be 2 by 6. So now what will be the probability that you will not get 5 or 6? So we can easily calculate 1 minus 2 by 6. Or we can also write this probability of 1, probability of 2, probability of 3 plus probability of 4. So instead of adding all these, we will be easily able to calculate this 4 by 6. So and the answer of this is also 4 by 6. So this is the rule that the total probability is equal to 1. 1 minus probability, because the total area is equal to 1 minus probability of x is less than 65. So when you subtract this whole area until 65 from this minus infinity, you will get this thing. Okay, so you not need to be confused with this. Then we want to transform, because this is normal distribution, we want to transform this normal distribution to the standard normal distribution, and you people know that standard normal distribution is equal to z is equal to x minus mu, and the standard normal distribution mean is equal to 0, and this is z. Instead of this one is x. Okay, so when we transform this, so we will put these values. So x minus mu, x is this 55 minus mu, which is 61, mean is 61, divided by standard deviation. This is the standard normal distribution formulation 2 plus 1 minus z is less than, now this is 65 minus 61, 61 is the mean divided by standard deviation 2. So when you simplify it, it will be z will be less than minus 3 plus 1 minus p, probability of z is less than 2. So now we need to calculate this minus 3 and this 2. So you already know that how to calculate these areas from the z table. So I am just going to show you that how you will calculate the area for minus 3 and for 2. So you can see this is a standard normal probability table. We are looking for the z is equal to minus 3. So z is equal to minus 3. This is the value, which is 0.0013. So you need to remember this. And the other value is z is equal to 2. So just come down. Z is equal to 2. Z is equal to 2 value is 0.9772. 0.977. So you can see for minus 3, which is 0.00135 plus 1 minus 0.97725. We already locate these values in the z table. When you simplify it, this will be equal to this one. So it's mean 2.4% of the cane are defective. So the inspector already calculate the process capability. They claim for that we need 3 sigma level, but inspector, when he visit it, when he collect sample and when he check, so the process capability, the process of that organization, the process of that industry is not capable for 3 sigma level, and they producing 2.4% of the cane in their production. They producing defective cane and the probability is 2.4%. So I hope you understand this. There is another example which is an assignment for you. This is the same example. Consider the capability of a process that put pressurized grease in an aerosol cane. The design specs call for an average of 60 pound per square inch of pressure in each cane with an upper tolerance limit of 65 and lower tolerance. A sample is taken from the production and is found that the cane's average is 61 psi. So this mean is also same just like in the previous example with a standard deviation of 2 psi. Suppose another process has a sample mean of 60.5. So now they only change, before it was 61, now they change the mean 60.5. And now they also change the dispersion, they also change the deviation. Now before it was 2, now it is 3. Now you need to check. Also use the Q1 macros, also construct a histogram. So please do it. In this way you will understand the process of 6 sigma, 3 sigma, 4 sigma clearly. So now you need to tell me, this is your assignment and you will submit this assignment to me, that is the process is capable for this mean 60.5 and for this standard deviation for 3 sigma. Which process is more consistent, the other one or this one? So you can easily construct, you can easily solve this example. Okay, there is another example computing the CP value at Coca Fish. 3 bottling machines are being evaluated for possible use at the fish plant. The machine must be capable of meeting the design specification of 15.8. So this is lower specs, 16.2 ounce. This is upper specs with at least a process capability index of 1. So CP is greater than 1. So these are 3 machines. The first machine sigma is 0.05. The second machine sigma is this one. The third machine, which is C, sigma is this one. Now this is upper and this is lower. So this is the difference between, this is the difference of these machines, upper tolerance limit and lower tolerance limit. And 6 sigma, so when you multiply 6 into 0.05, it will be 0.3, because we want to check it for 6 sigma, because we want to calculate CP. So the machine ACP is 1.33. Yes, the machine is capable for this sigma, and you can see the sigma value is very low. So this is basically indicating you when the standard deviation in a specific data is low, it means there is very little risk involved. So that is why the process capability of machine A is capable 1.33. So yes, it is capable for 3 sigma, but it is still not capable for 6 sigma, because 6 sigma, if the CP value is near to 2, then we can say that this machine is capable for 6 sigma, 6 standard deviation. Let me check it now for machine B. Machine B, the data are given. So when you put these values in the CP formulation, you will get 0.67. So machine B is not capable for 3 sigma. Machine C is also not capable. Even it is not capable maybe for 2 sigma. You can also check it for 1 sigma. It will be capable for 1 sigma. So at this way, you will calculate the 6 sigma, 3 sigma and 4 sigma. Computing the CPK value at Coca Fish. So in the last slide, I just calculated CP. Now we want to measure CPK, because CPK, as I already mentioned to you, CPK can never exceed CP, and CP is just an upper bound for CPK. So let me calculate CPK for this one. So the CPK design specification call for a target value is 16 plus minus 0.2 ounce. Plus minus 2 mean 16 plus 0.2 will be the upper bound and 16 minus 0.2 will be the lower bound. Just like I already mentioned. Observed process output has now shifted and has a mean of 15.9 and sigma is 0.1. So now this is, let's suppose, the mean of the process and this is the sigma. So let me put these values in this formulation. So when you calculate it, CPK is 0.333. So CPK less than 1, revealing that the process is not capable. So at this way, you will calculate the specification tolerances. You will calculate that is the process capable, is the production or the service industry which they following, which they taking is capable or not.